distributed service framework, which provides distributed and highly available coordination service capabilities. In this part, we will talk about what is Zookeeper and its architecture. First is the Zookeeper overview. The Zookeeper distributed service framework is used to solve some data management problems that are frequently encountered in distributed applications and provides distributed and highly available coordination service capabilities. In security mode, Zookeeper depends on Kerberos and LDAP server for security authentication, but in non-security mode, Zookeeper does not depend on them anymore. As a bottom layer component, Zookeeper is widely used and depended by upper layer components, such as Kafka, HDFS, HBase, and Storm. After a brief introduction of Zookeeper, next, let's talk about its architecture. The Zookeeper cluster consists of a group of server nodes. In this group, there's only one leader node, and other nodes are followers. When the client is connected to the Zookeeper cluster and initiates a write request, the request is sent to the leader. After receiving a data change request, the leader node writes the data to the disk first and then to the memory. Then data changes on the leader node are synchronized to the followers in the cluster. The leader is elected during the cluster startup. Zookeeper adopts a protocol named Zookeeper Atomic Broadcast, short of ZAB, which ensures the data or status consistency among nodes in the coordination system. Followers use ZAB to synchronize data from the leader and then provide services based on local storage. So we know that there should be a leader in the cluster. During leader election, if an instance obtains more than half of the votes, the instance becomes the leader. For a cluster with n servers, n may be an odd or even number. When n is an odd number, assuming n equals to 2x plus 1, then the server needs to obtain x plus 1 votes to become the leader. So the disaster recovery capability is x. When n is an even number, that is, n equals to 2x plus 2, then the node needs to obtain x plus 2 votes to become the leader. Now the disaster recovery capability is also x. So the disaster recovery capability of 2x plus 1 nodes is the same as that of 2x plus 2 nodes. Considering the election and writing speed, it is recommended that an odd number of nodes be deployed for Zookeeper. Next are some key features of Zookeeper. First is the eventual consistency. It means that all servers are displayed in the same view. Second is its real-time capability. Clients can obtain server updates and failures within a specified period of time. Third is the reliability. It means that once a message is received by one server, it will be received by rest of the servers. Fourth is the wait-free feature. Slow or faulty clients cannot intervene the requests of rapid clients, so that the requests of each client can be processed effectively. Fifth is the atomicity. It means that data update either succeeds or fails. There are no intermediate status. Last is the sequence consistency. It means updates sent by the client are applied in the sequence in which they are sent. According to the consistency of Zookeeper, the client obtains the same view regardless of server connected. Therefore, read operations can be performed on any server. As for the write process, just as the figure shows, a client can initiate a write request on any server, which is similar to the reading process, and the server will send the request to the leader. Here, node ZK2 is the leader. After receiving the write request, the leader sends the request to followers and asks the followers whether the write operation can be performed. The followers send back a ACK message based on its own condition. If the number of servers that write operations can be performed is greater than 50% of the total, the write operation can be performed. Then, the leader performs the write operation and data is synchronized to the followers. Until now, the write operation is complete. Here are some common commands for Zookeeper clients. If we want to invoke a Zookeeper client, we can run such command. Here, 172.16.0.1 is the IP of the server, and 24002 is the port of the instance. We can use create to create a node, use ls to list subnodes, use set to create node data, use get to obtain node data, use delete to delete a node. This is all about Zookeeper. And in this chapter, we talk about HDFS and Zookeeper. The distributed file system is an effective solution for large-scale data storage in the big data era. The open-source HDFS implements GFS and distributed storage of massive data by using computer clusters formed by inexpensive hardware. HDFS is compatible with inexpensive hardware devices, stream data read and write, large datasets, simple file models, and powerful cross-platform compatibility. Block is the core concept of HDFS. A large file is split into multiple blocks. HDFS adopts the abstract block concept, supports large-scale file storage, simplifies system design, and is suitable for data backup. And zookeeper distributed service framework is used to solve some data management problems that are frequently encountered in distributed applications and provide distributed and highly available coordination service capabilities. Okay, there are some questions. First, why is it recommended that the number of servers in zookeeper cluster be deployed in an odd number? Actually, in such deployment mode, the disaster recovery capability between odd and odd plus 1 is the same, but the deployment cost is lower. Second, why is the HDFS data block size larger than the disk block size? Well, such design is to minimize addressing overhead. Third, can HDFS data be read when it is written? When data is being written, the block is invisible to other readers, but the metadata is immediately visible in the namespace. When more than one block is written or the writing ends, the data is visible to a new reader. Thank you for learning this chapter, and in next chapter, we will continue with the distributed data warehouse type.